Hi, my name is Dohle, and I'm going to present work and energy. And the way that I'm going to present this is in the way, basically I'm going to derive work and energy from Newton's second law. And the purpose of doing this is to show how work and energy is actually just using Newton's law with rectilinear motion. And if you have a good grasp of rectilinear motion, work and energy should fall right out. And I'm going to show you how that works. And I'm going to start with Newton's second law, which states that the force equals the mass times the acceleration, the sum of the forces. And so we have our force. Let me draw. No, I'm just going to. We have our force in the x direction equals mass times the acceleration in the x direction. And we know that we read the textbook and we see this equation for work and energy. We see that the work from position 1 to position 2 equals the kinetic energy final minus kinetic energy initial. And then the kinetic energy final equals 1/2 mvf squared minus the kinetic energy initial, which is 1/2 mvo squared. But what does that mean? Why do we, where does this come from? And why do we use it in this form? And well, we know that work is the force in the x direction times the position in the x direction. And I'm going to show you how the work and energy equation pops right out of Newton's second law. And it's not actually very difficult. And so we're given, in our problem, we're given a force, or a couple forces. You have to sum them up and break them up into components. But basically you're given forces, you're given distances, and you're given velocity. So whenever you're given these, you're trying to figure out how this is related to Newton's second law. And the way to relate it is with the acceleration. If you'll recall from rectilinear motion, acceleration is related to velocity and it's related to position. And so we'll recall that acceleration equals the change in velocity over the change in time. We'll also recall that the velocity equals the change in distance over the change in time. With a little algebraic rearrangement, we see that the change in time equals the change in position over the velocity. It's getting abstract at this point, but it's true because algebra is true, because physics is true. Now we're going to substitute dx dv in for dt in the acceleration, and we get that the acceleration equals the velocity times the change in velocity over the change in distance. And you're going to have to plug that in and go through the process, but this is what you should do for when you solve your rectilinear motion problems. It makes it a lot simpler. You don't have to remember all the different equations, this and that, and at the same time, it ends up telling you what your initial and final conditions are when you go in and integrate. So we're going to substitute our v dv dx in for a. And why are we doing that? Why do we know that we can do that? We know because we're solving a problem in terms of velocity and in terms of position, right here. So now we take this, substitute it in for our acceleration. Now our equation is starting to look a little bit better. Our force in the x direction equals mv dv dx. A little algebraic manipulation. F in the x direction times the change in the position equals the mass times the velocity times the change in velocity. And we can see clearly now that we're going to our variables are going to pop out of here because everything is in terms of forces, positions, and velocities. So no matter what we're solving for, we're going to be able to see it come out of here. And so how does it come out? It comes out by integration. We're going to sum up all the forces times all the distances and all the masses times the velocity times all the changes in velocity. And so our initial position, generally, depending on how we set up our axes and how we do it, I try to set up my initial position as 0 to simplify the problems. And our final position is some position, xf. Our initial velocity is usually some velocity, and our final velocity is some different velocity. And so when we integrate, we get f in the x direction times the change in position in the x direction equals 1/2 mv squared, mvf squared, sorry, minus 1/2 mv sub naught squared. So you can see we have our work equals kinetic energy final minus kinetic energy initial. And so as I'll demonstrate in some future, in at least one future example, I'll show you how you don't need to memorize this at all. All you need to do is start with Newton's second law. And an advantage to starting with Newton's second law, sometimes you don't even have to go all the way down to your work and energy equations. Sometimes you can solve for acceleration directly using your rectilinear motion, A equals V, dV, dx. With acceleration solved for, you'll be able to solve for your other variables. Thank you.